Thank you so much. And first of all, I would like to thank Professor Shastri for inviting me to be here. It is the first time for me to be in India. I really enjoy my staying here, and it is a great honor to give a talk here. Since my talk is a little bit far from the mainstream of the conference and main discussion on group theory and computational group of theoretical point of view, so I will try to give this talk. By using a simple explanation from graph theory, group theory, gray code theory, and actually I will try to discuss some open problems which comes from graph theory and graphs on groups, and I will show what is the connection between Cayley graphs and gray codes, and to discuss some open problem in this area. And maybe I will give some applications from coding theory, from bioinformatics, because the Cayley graphs, which will be discussed during this talk, they are used to be applied in computer science. So what is my plan? First of all, I will give some definitions from graph theories, then we will talk about Cayley graphs, and I will show what is the connection between Hamiltonicity of Cayley graphs and gray codes, and then we will talk about some special combinatorial gray codes which are considered nowadays. So let me start with maybe some simple definitions, but I need them. So I will start from graph theory, yeah? From graph theory. What is, well, we consider that gamma is a simple graph, and as usual, what is the definition of a graph to be Hamiltonian? So we said that gamma is set to be Hamiltonian if it contains Hamiltonian cycle or path. It depends, yeah. So Hamiltonian cycle or Hamiltonian path. And what is it? Well, as usual, Hamiltonian path means that it is a path or a cycle which contains all vertices of a graph without repetitions, and exactly once. And it is known that actually the problem of Hamiltonicity, what does it mean Hamiltonicity? Well, Hamiltonicity. That is the problem or the question to check whether a graph has a Hamiltonian cycle or a Hamiltonian path. So to check whether a graph has a Hamiltonian cycle or path. And actually, it is known that this problem is NP complete. So it was shown, I don't know, maybe it is possible to find in the book written by Gray and Johnson. So Gray and Johnson, it is known that this problem is NP complete. It is known that it is, complete. And actually, we are interested on Hamiltonicity on Cayley graphs. What does it mean, a Cayley graph? Let me give you a definition. So Cayley graph, what does it mean? What we have? So it is a graph on a group. It is a graph on a group. And what we have? So we have a group G is a group, and say let S is is a subgroup of, is a subset of a group G, such that, well, it is generating set, is a generating set, such that it is identity free. So it doesn't contain identity, so identity free. It is identity free, and it is symmetric. It should be symmetric. So S should be equal, should be coincide with its inverse element. So if S is in the generating set, this means that its inverse also should be in this set. And what are the main properties of this graph? Properties. Well, of course it is connected graph, it should be connected. So it is connected, it is trivial because since G is generated by the set S, this means that G is connected, so is connected. And it is regular, and the degree of each vertex is equal to the cardinality of the generated set. So it is regular. And of course it is it is vertex transitive. It is vertex transitive. The main properties of Cayley graph. What is a simple example? Well, if you take any group, say, if you take a symmetric group and say, let me consider that is star graph. So it is so-called as star graph. It is a Cayley graph on the symmetric group, which is generated by the set of all transpositions, transpose the first element and I element, where I is between 2 and n. So that is one of the example of Cayley graphs, which will be considered a little bit later. And well, another example. Say if you take a hypercube, yeah, a hypercube. So hypercube is a Cayley graph on a group of all binary vectors of length n, and if you take a generated set, which is actually as a standard basis of this vector space. So if we take all vectors of the following view, so 0 up to 1 in the east position, and then 0 and so on, so that is a standard basis. Standard basis. So it is a Cayley graph. Actually, it can be considered from another point of view. Hypercube can be represented as n copies of K2, where K2 is the complex graph on two vertices. So times n times, it is another representation, the same graph. And it is also isomorphic to two copies of the previous the hypercube of the previous order, n minus 1. What does it mean? What does it mean? Okay, say if n, one more example for this example, yeah? If we take n is equal to 1, this means that what we have. So we have two elements, we have two vectors of length 1. This means that we have 1 and one vertex corresponding to 0 and one vertex corresponding to 1. So there is an edge if and only if two vectors differ just in one position. That is so-called Hamming distance. Well, Hamming distance. So we use distance between two vectors, x and y. It is It is the number of different positions. Well, not correct. So the number of positions where x and y differ. So in this case, we have an edge because they differ just in one position. Now, what is the next? The next step, say, n, if n is equal to 2, what is the way to get the new graph? So it is, say, it will be h1. H1. Now, how it looks like a hypercube on vectors of length 2. So we need to take 2 copies. By using this definition, we need to take 2 copies, 0, 1, 0, 1 here, and here is edge. And actually, we have to consider all binary vectors of length 2. So what is the way to construct it? So we put a 0 for these vectors and 1 for these vectors, and we get the new graph hypercube of order 2. And it is exactly 2 copies to Cartesian product. It is Cartesian product of H1, or it is the same as K2, right? K2 and K2. And so on. We can continue for n equal to 3 by using 2 copies of the previous graph. If I take 2 copies of the previous graph, say it will be a hypercube with numbering 1, 0, 1, 1, 0, 1, and 0, 0, and 1 more copy. So I'm taking 2 copy, and what I have here, say it will be the same. 0, 1, 1, 1, 1, 0, 0, 0. So what is the way to get a hypercube and all binary vectors? I just put 0 for all of these vectors, and I put 1 for the second copy. And we will get all binary vectors. So that is the way to construct this graph, which means that a hypercube H3 is isomorphic to 2 copies of H2, or it is the same as we consider 2 K2 times K2 times K2, so 3 times. Now, you see, if we will come back to Hamiltonicity of graph, it is well known that a hypercube is Hamiltonian. And one of the way to show why it is so is the following one. There is one-to-one correspondence between Hamiltonicity of hypercubes and gray codes. What does it mean, gray codes? So, by the definition, a gray code is a sequence of binary vectors so that two successive vectors differ just in one position. So that is the definition of binary gray code. And what is the way to get it? Say, of course, there are many ways to do this, but if we consider binary reflected gray code. What is the well-known algorithm to do this? say n equal to 1, what we have? We have to take a sequence of all 2 prime n binary vectors. So we have to take 0, 1, that is the sequence. And what is the way to get gray code? So this is gray code of size 1. And now, if I want to consider, if I want to get a gray code of order 2, then I take 0 and 1 for one side, and then I reflect, and I put 1 and 0 here. And I put 0 for all vectors from the left side and 1 to the right side. So it will be a gray code of length 2, and so on. But if you have a look on this sequence, so this sequence of these 4 vectors, actually it is the same as we will take a Hamiltonian cycle for H2. It is trivial almost. But if you consider the case when n is equal to 3, what it will be in this case. So again, I have to take 4 vectors of the previous size, so 0, 0, 0, 1, 1, 1, 1, 0, and then I reflect, and again I have 4 vectors, but reflected on this line. So I put 1, 0, 1, 1, 0, 1, and 0, 0. And now for left part, for the first position, I put 0 here, and I put 1 for the second part. Now, if you will have a look on this sequence and on the hypercube of size 3, so we start with these vectors, and then we go to the next one, and then go to this vertex, and then to this one. So we use all vertices from one copy. And what does it mean that we reflect it? Reflect means that we go to another copy. And starting from this point, from this vertex, I have the new Hamiltonian. It is a part of Hamiltonian cycle. But finally, I come back to the initial vertex, and I have got a Hamiltonian cycle. So that is the way to show that there is one-to-one. There is one-to-one correspondence between Hamiltonicity or Hamiltonian actually cycles in this case, Hamiltonian cycles, and binary reflected codes. Binary reflected codes in hypercube graphs. Actually, starting from the middle of 17th of the last century, people starting to interested to some generalization of gray codes. And nowadays, one of the direction in this area is to try to find some combinatorial gray codes which allow to enumerate some combinatorial object. So combinatorial gray codes. For example, it is possible to find a good review which was written by Savage in 17th. And what are the object, combinatorial gray codes? What is the main idea? The main idea is the following one. You have some discrete objects, and you would like to to enumerate all of them so that the difference between two successive elements is just one in some sense, which means that you need to have some metric on these combinatorial objects and then to enumerate them so that all successive elements will be in distance one in some sense. What we can do, which kind of objects can be considered? Say permutations, then sets, and even matrices, Say, let us consider which approach I used to enumerate permutations and why it is why it is connected to Cayley graphs. So here I started to give some examples of Cayley graphs on the symmetric group, and so now let us consider gray quotes on permutations, and Hamiltonicity of Cayley graphs on the symmetric group with some generated set. So it depends. It depends on the generated set which graph you will get. What it is known in general? What are the general results about Hamiltonicity of Cayley graphs on the symmetric group? One of the first results was obtained in 1975 by Koppelmacher, and Liskowitz. And almost at the same time, it was published in 1979 by Peter Slater. The following result. Actually, they didn't consider Cayley graphs on the symmetric group. The main idea was to find an algorithm which allowed to generate all permutations without repetitions. So it was the main idea. And from Cayley graph point of view, they have got the following result. Say, let G is the symmetric group, and S is the set of transpositions. Then Cayley graph gamma on the symmetric group with this generated set is Hamiltonian. In which sense? Because you see, actually, you can get a Hamiltonian cycle, Hamiltonian path. So Liskowitz and Koppelmacher, they proved that it is Hamiltonian in sense as path, but Slater proved that it is Hamiltonian as cyclic. Moreover, from the result by Slater, it follows the following thing, that actually for any two vertices, say U and V from different paths. What does it mean from different paths? Actually, you see, since we have a graph on the symmetric group and it is generated by transpositions, this means that this graph is bipartite because any transpositions change the parity of the permutation. So you have one part of odd permutation and another part of all even permutations. So if you take U and V from different parts of V, say, if V is a union of two parts where V1 is presented by odd permutations, and say V2 is presented by even permutations. There is a Hamiltonian UV path in graph generated by transpositions. So it is known that for any Cayley graphs on the symmetric group generated by transpositions, this graph will be Hamiltonian. But what is interesting from Gray-Cott's point of view? The main interest is to find some sequence which will enumerate all permutations so that you will get a combinatorial Gray-Cott on permutations. So what it is known and what it is done. There is one more interesting example of Cayley graphs generated by involution. It is the so-called pancake graph. What it is? The name comes from the pancake problem. And what is it? So you have a stack of pancakes, yeah? So say it is a stack of pancakes. And you need to reorder. They have, all of them have different size. From biggest one and up to the smallest one, say it will be 1. And you need to reorder all these pancakes of different sizes so that you will get the smallest one on the top and the biggest one on the bottom, such that you will get the picture like this one. So if we use numbering so that the pancake of the biggest size will have n and up to the smallest one corresponding to 1, when it will be reordered, so reorder it, you will get the stack starting from the smallest one and with the biggest one on the bottom. So what we have, actually, if we will use representation of all these pancakes as a permutation, so we have here a permutation pi 1, pi 2, and so on up to pi n. And here, what we have here, well, we have the identity permutation right here. So it is identity permutation. Identity permutation. This identity permutation. And what is it? Yeah, what is the main idea? What is the way to reorder? Yeah, so you have all these pancakes, and the only way for you is to grab all some set of pancakes and to flip them so that the order of pancakes will be inverse in this interval. And this operation is called as flip. By flip or prefix reversal. On the permutation language, this means that say you have a permutation pi 1, pi 2, so on, pi I minus 1, pi I, and pi I plus 1, and so on, pi n, and say prefix reversal Ri, where I is between 2 and n. If you apply Ri, then you will get a permutation so that all elements inside of this interval will be inversed. So you will get a new permutation starting with pi I and so on, pi I minus 1, and so on up to pi 1. And here you will get the rest, which will be the same, pi I plus 1, and so on, pi n. And the pancake problem is to find the minimal number of flips so that you can reorder any stack of pancakes as you would like to get. So to find the minimal number of flips so that to reorder any stack. From graph theoretical point of view, this means that what we have from Cayley graphs, see, yeah? From Cayley graphs. What we have? Actually, we have the pancake graph, which is defined in a Cayley graph on the symmetric group generated by the set of all prefix reversals. And the pancake problem is to find its diameter. So the pancake problem is to find its diameter. Still, it is open. And why explain this problem and the definition of this graph? Because for this graph, some new prefix reversal codes were suggested recently, and there are some open problems on this graph. So now I'm ready to give you some open problems and conjectures in this area. Well, the first conjecture. Well, actually, it is general one. That any vertex transitive graph is Hamiltonian. Hamiltonian in the sense that it has Hamiltonian path. Conjecture number 2, that is, well, actually people say that it is Laszlova's conjecture, But actually, he asked another question. He asked about the following property of vertex-transitive graph. Does every vertex-transitive graph have Hamiltonian path or Hamiltonian cycle? But nowadays, this conjecture is more famous and used. Another conjecture is the following one. When conjecture 1 was posted, people have found that there are some graphs which have Hamiltonian path but not Hamiltonian cycle. They are vertex transitive. Well, this graph is well known. That is the Peterson graph. Peterson graph. It is vertex transitive. It is vertex transitive. It is known that it is not Cayley graph. Not Cayley graph. And it is also known that it has Hamiltonian path, but not cycle. Not cycle. Not cycle. So the new conjecture was stated as follows: that any Cayley graph is Hamiltonian. Is Hamiltonian as a cycle. And still it is also open. So it is open. It is open. For the pancake graph, it is known. So let me come back to the pancake graph. For the pancake graph, it is known that it is Hamiltonian. It is Hamiltonian. Properties of this graph. Well, it is known that it is Hamiltonian. Moreover, it is known that it has a very complicated cycle structure, and the N has well, let me write in other way. Any L cycle where L is between 6 and n factorial can be embedded in the pancake graph, where n is at least 4. What it means is that starting from 6 and up to n factorial, all of these cycles can be embedded to the pancake graph. It is also known, well, it was this result, the last one, it was shown by Konevsky and Feng in 1995, and also Xu in 1999. Recently, so it is known that it is Hamiltonian, that is important, but is it possible to get any combinatorial gray code on this graph? And recently, in 2013, it was shown by Aaron Williams and Joy Savada, that it has, so the pancake graph has two so-called greedy prefix reversal gray codes. To construct these codes, they use the following greedy by using greedy sequences. sequences. So that if you start with the biggest prefix reversal Rn, and then you use it as long as possible, then you have to use the next one, Rn minus 1, Rn minus 2, and so on up to R3, R2. So this sequence will give you a prefix reversal gray code in this graph, which will correspond to the Hamiltonian cycle. So it is the first one. And the second one, just inverse the sequence. And you will also get a Hamiltonian cycle and a greedy prefix reversal gray code. But actually, this code was presented in 1979 by Sachs, who also suggested an algorithm to generate permutations without repetition. And these two sequences given two different gray codes gives us one more conjecture that conjecture by Williams and Sawada that there are no other prefix reversal gray codes. One more interesting graph was recently considered by Sadborough. Well, Sadborough. 2013. So just consider the following graph. If you take the symmetric group and consider generated set presented by only three big prefix reversals, Rn minus 1 and Rn minus 2, they proved that it is connected. Well, it is a Cayley graph and it is connected. So the question and conjecture is the following one. It was given by Williams and Sawada this year. They say that for any n, this graph, there is a special name for this graph. It is called as three big pancake graph. For any n, three big pancake graph has a greedy gray codes on these three prefix reversals, Rn minus 1, and Rn minus 2. There's one more generalization. So actually, when you consider the pancakes, some of them can be burned. And in this case, you can consider so-called burnt pancake problem. So you have sign permutations and consider Cayley graph on sign permutation and what is the diameter of this graph. So it is so-called burnt pancake problems, which was stated by Bill Gates and Papa Dimitrov. And Williams and Sawada also ask, if we will, instead of permutations, if we will take sign permutations, other greedy codes on sign prefix reversal. So that is also the open question. And I think that I can stop here because I have just 7 seconds. So thank you so much.
Questions?
No. Not randomly. Oh no, just you take a permutation. Since well, since any killing graph is vertex transitive, doesn't matter what is the first vertex you will start. Say if you start with identity permutation, that you don't need to consider the structure of the graph. You are looking for the algorithm which will generate all permutations without repetitions, but by using one and the same approach. So this greedy sequence means that you start with your permutation, say identity 1, and say let us start with identity permutation on 5 elements, 1, 2, 3, 4. Well, so what do you have to do? You can apply an R5 just one, yes? So you will inverse on all elements, and you will get the new permutation. Now you cannot use this the same generating element. So you have to use R4, right? Yeah. Then you will get the new permutation 2, 3, 4, 5, 1. Now again you can use R5, right? Yeah, you can use it because it is greedy algorithm. Then you will get the new permutation, which will be as 1, 5, 4, 3, 2, and so on. As long as possible to get new permutations without repetition by using R4 or R5. When it will be not possible, then you will get the next element from your sequence. That is the main idea. And actually this idea based on the so-called hierarchical structure of this graph, because as it was shown for the hypercube, so hypercube is isomorphic to n copies of the previous hypercube, right? But for the pancake graph, we have the following situation. Oh, sorry, 2. And for the pancake graph, the next one is obtained from n copies of the previous one. So, say what it is P3, it will be just 6 cycle. It will be 6 cycle. And so it is 6 cycle. And if you take 4 copies of P3, then you will get P4, the pancake graph on permutations of length 4. And you will construct this graph by using 4 copies of the previous size. And it will have something like this picture. So here you will have all permutation with ending with, say, element 1 as the last position, right? All permutations. And all permutations ending with 2 at the last position, and the same here and here as well. And there are some external edges corresponding to R4, because what we have here are 2, R3, R2, R3, R2, R3. That is the way to get it. because we have just 2 generating elements. But in this case, we have 3 generated elements, and the last one corresponds to external edges to these subgraphs. So the picture will be like this one. And this graph has so-called hierarchical structure, which means that if you start, say, from this, I'm not sure that I will get Hamiltonian path, but the main idea is that you started to use one and the same elements up to here, then you come to the next copy and you end it with the last vertex from this copy, and then you go to another one and so on. So that is the main idea.
Further questions? And if not, I'd like to thank the speaker again for a nice talk.